Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So welcome, everyone. Thank you for coming. It's my great pleasure to introduce Hao Chen to give a talk today on the hardness of problems underlying homomorphic encryption. Hao is a PhD candidate at the University of Washington in number theory, working with William Stein. He's contributed to the SAGE math project, and he's made significant contributions to understanding the security of the RLWE problem, which is important for applications such as homomorphic encryption. So thank you, Hao.
Thanks. All right, so thanks for coming. It's good to be back. Today I'm going to talk about hardness of problems underlying homomorphic encryption, and the subtitle is a survey on Ring-LWE cryptography. So I plan to do both. So a little bit about myself. So Kristin already said a lot. So maybe I'll just mention that I had a fantastic time last summer, intern at MSR here, and I worked on this RLWE cryptography. So that's sort of my first entry into this subject. And since then I've been working on it. It's truly amazing and a lot of fun, right? So let's, before I start the talk, maybe I'll give a little overview of the structure of the talk. So we have three parts here. The first part is the introduction, where I'm going to talk about the basic ideas of homomorphic encryption and the learning with errors problem. And in the second part, I'm going to introduce the ring learning with errors problem, the definitions, and the hardness in the classical papers. And in the third part, I'm going to give a survey on attacks on ring learning with errors. This include the already known attacks on RLWE and the new attacks we developed over the last summer and since then. And then I'm kind of, in the end, give a summary of the current security situations of RLWE problems and possibly future directions. OK, so let's get right into it. OK, so homomorphic encryption, what is it? So the scenario is like this. So suppose Allison is a user who wants the cloud to process her data without exposing her data to the cloud. So this is a very general scenario because usually you would have some sensitive data that you don't want to reveal to people, but you still want to outsource the computation. So formally, if you have data x and a function f, and you want to compute f of x, so what you would do is to encrypt the data x and send the encrypted data and the function to the cloud. And the cloud, not knowing what x is, must choose some other function, big F, to evaluate on this encryption of x, such that when it sends back f of encryption of x, and you decrypt it, then you get your function value back. So at the end of the day, everyone's happy. So the question, of course, is that whether this is possible at all. So, well, then people. So first, if you want to ask this question, then maybe you want to ask what kind of f do you want to evaluate. So suppose you have an encryption function, then maybe the most immediate choice of function class is the polynomials. So it turns out that, well, if you can do the addition and multiplication operations on the encrypted data, then you can evaluate all polynomials, at least theoretically. So, and in theory, this is called fully homomorphic encryption. So that's just a name for it. And you see the property is that you want two operations that mimics plus and multiply on the encrypted data such that when you do the operations, they correspond to the usual addition and multiplication on the plain text. So homomorphic encryption has a lot of applications. So basically, if you have any kind of sensitive data, then it will be a place where you can sort of apply homomorphic encryption. So examples include predictive analysis of private medical data, and the CryptoNet project, which is a successful project of Microsoft, including this machine learning algorithm neural network, and you evaluate a trained neural network over unencrypted data. and predictive analysis of genomic data, encrypted databases, statistical calculations, and biometric authentication. Homomorphic key management. So this is something I just learned yesterday when I was searching online. So there's this company, Porticore, which claims that they have this homomorphic key management. So, which sounds a little interesting to me because, so I just downloaded their white paper, but basically they're trying to say that they're using homomorphic encryption to manage users' keys, but not for the cryptography part. And then also other applications including multi-party computation, secret sharing scheme, and election schemes, etc. So you can see that there's a lot of there's a growing area of applications of fully homomorphic encryption. So, and is this possible? And in a very groundbreaking work in 2009, Craig Gentry, in his PhD thesis, proved that theoretically there is a way to do fully homomorphic encryption. And the way he does it is use encryptions and apply ideas in ideal lattices to the problem. But the problem with this original proof of Gentry is that it's very impractical. In particular, there's this one very central gradient of the proof that uses a technique called bootstrapping, which is very, very inefficient in practice. So people have been thinking about how to improve homomorphic encryption schemes since then. And there has been tons of theoretical research. And actually, since 2010, up to today, a lot of way more efficient schemes has been developed by various people. And up to now, the most promising homomorphic encryption schemes, they all base their security on two problems that are derived from from the standard lattice problems. One of them is called learning with errors, which we will abbreviate with LWE. And the other one is sort of an extension of that problem, which we call Ring-LWE. And they are developed introduced in 2005 and 2010, respectively. So that's what we'll focus on the rest of the talk. And the examples of homomorphic encryption schemes using based on these two problems are one scheme made by Lyubashevsky, Gentry, and Katherine, and the Yashi scheme by Boss, Lauter, Lauter, and Eric. So let's talk about what is the learning with errors problem. So this is one screenshot I took from Regev's 2005 paper, and I think it's a very intuitive demonstration of what the problem actually is. So you're given a prime q and a positive integer n, and your secret is a vector with value in the finite field fq. So here it's denoted by zq. So this is the secret, and you're asked to solve the secret given a sequence of linear equations. But these linear equations are not exact in the sense that, so if you look at the first equation, modulo 17, this is only approximately equal. It means that this value here can be 8, or it can be 7, or it can be 9, or some other values around 8. So then what it means is that even if you're given, so here, even if you're given more than 4 of the equations, it's not guaranteed that you can solve for the secret using this system because because this is not an equality sign. So the problem is posed in this way, and that's the learning with errors problem. So that's not the central topic of my talk, so I'll just talk briefly about what's the hardness result for RLWE. So this is proved in by Regev in his 2005 paper. Solving an n-dimensional RLWE when the modulus q is polynomial in the dimension n implies an equally efficient solution to a hard lattice problem in dimension square root of n. So I'll talk more about, in one of the later slides, what are the hard lattice problems we are talking about. But basically here, if you want to have, you need to have a square root reduction. So this lattice problem gets harder when the dimension is larger. So here you don't really get an equality. And saying a lattice problem is hard just means that the best known algorithm is not polynomial in the dimension. or rather it's exponential or sub-exponential. And if you allow quantum algorithms, then you can replace square root of n by n. So, which means that in a world where we have quantum algorithms, this LWE problem is at least as hard as the hard lattice problems of the same dimension. So that's the main hardness results for LWE. And now let's talk about what is Ring-LWE. So when people developed this idea of Ring-LWE, the motivation was to make the LWE-based homomorphic encryption schemes more efficient. So somehow, using this scheme, you can pack more information into a plain text. So encryption becomes more efficient. So let's review the classic setup of Ring-LWE. So here you take the dimension n to be a power of 2. And you take modulus q to be a prime, which needs to be congruent to 1 modulo 2n. And your ring R is the polynomial quotient ring of the polynomials in one variable with integer coefficient modulo this polynomial xvn plus 1. OK, so now the problem is you are given the secret s of x as a polynomial in this ring. And your goal is to solve for this secret polynomial using a random noisy system. So here the situation is sort of similar to the LWE setting, but here you have random coefficients a of x, which is sampled uniformly from this ring R. And you have small secret polynomials ei of x, where so these ei's are unknown. And also, like if you know one of the errors is 0, then this becomes a trivial problem because you can just divide by, say, a0. And the real hardness of this problem is that you don't know what these ei's are. And just by the way, when I say error, I mean these polynomials have small coefficients. So that's the problem. And how hard is this problem? Well, before we discuss the hardness, maybe I'll just try to generalize the RLWE problem to arbitrary rings. So here we're really using a very restrictive class of rings. So remember, n needs to be a power of 2. So it grows up very quickly and it's very sparse. And we have relatively few parameter choices. But actually, you can define this for fairly general situations. So we have essentially 4 parameters that we can choose: the ring R, the modulus Q, the error distribution chi, and of course whether the error is discrete and continuous. So I'll talk about this more, but it turns out to be a non-trivial assumption. So this 4th parameter is a Boolean variable. So okay, so here what's the ring R? So usually in this problem we take R to be the ring of integers of some number field, and in some of the in the most classical RLWE paper, they also use the dual ring of R instead of R. But in the case of 2-power cyclotomic field, which is what this ring is corresponding to, the two are essentially the same. And Q is, again, the prime. And continuous just means that do we use continuous error or do we use discrete error? And chi just represents a Gaussian distribution, whether it's in the n-dimensional Euclidean space or it's in R. So in the continuous case, we sample the Gaussian distribution in Euclidean space. And in the discrete case, we sample them in R. So I'll talk about how do we do that. And we denote spherical Gaussians of width R by dr. So the reason here is usually when people talk about these problems, they want to sample the error in a spherical way. So then how would you produce such a noisy sample? Well, in the continuous setting, you fix the secret to be an element of this quotient ring, which is a finite set of cardinality q to the n. You can think of it as that. And you choose A uniformly from R mod QR, and the arrow E from a continuous Gaussian on Rn. And then the sample you output will be A comma B, where B is equal to AS plus E. So here, the first coordinate is uniform, and the second coordinate, the goal is to make it look uniform inside this Rn modulo QR dual. So QR dual is actually via some kind of embedding becomes a lattice. So this is high dimension torus, and the error should be scattered inside that torus. So that's the picture. And in the discrete setting, basically almost everything is the same, but you choose your error from, you choose your secret from the original ring, not the dual ring, and you choose A uniformly and E from a discrete Gaussian on R. And the sample you output will also be A comma B, but now the sample will lie in a discrete set instead of a torus. So when you choose R to be the ring of integers of the 2-power cyclotomic field, this goes back to the previous definition of RLWE. Yeah?
Is it essentially the definition of a continuous error selection is that you choose from a continuous Gaussian and discrete Gaussian? Is that right?
Oh, yeah.
So can you expand on what those two mean?
Yeah, I'll talk about. So continuous Gaussian is a multivariate Gaussian distribution. And I think we need it to be spherical. And I'll talk about what's discrete Gaussian. So maybe this is not in my slide, but if you have an n-dimensional lattice in Rn, then you can give each lattice vector a weight, which is e to the minus the norm of the vector squared over some parameter. So you sample in this discrete set, and the probability of sample each vector is proportional to the weight. So for example, if you have, if the width parameter is 1, then you sample the 0 vector with probability e to the minus 0, which is 1, but then you need to scale everything so that the total probability is 1. But so that's what I think that's what I mean by proportional. So yeah. So yeah, but again, R is just a ring. Yeah, sorry.
So you might have said this already. Are these both variants that are proposed in existing papers?
So the continuous error is used in the original LPR paper in 2010, and the discrete error is used in a paper by Kristin and her co-authors in the 2015 paper in Crypto of attacking RLWE in different coming up with vulnerable instance of RLWE in number fields.
The proposed schemes fall in the first category.
The
proposed schemes fall in the first category.
The proposed scheme in the
the constructions that people are proposing is secure.
Yeah. So I mean, in practice, what people use is this discrete version because it's easier to handle.
But what they write about in paper is the continuous.
Right.
Yeah, and the point is they're the same. In practice, we use this all the time. Z adjoint related to the D, and they're the same there.
Okay.
But for other rings, they're not the same.
But didn't LPR already discuss the discrete case?
Very briefly.
Very briefly.
Yeah. They talked about whether they sort of imply that discrete is as hard as continuous when the error is large enough, but they didn't give explicit proof. Okay, so I'll talk about how to put a discrete Gaussian distribution on this R, because R is not a lattice yet, but we're going to make it into a lattice. So maybe I just give some backgrounds on number fields and number rings. So number fields are finite extensions of the rational numbers. So examples are like Q adjoint square root of 2, Q adjoint the root of -1, or Q adjoint the mth root of unity. And the number ring are the ring of integers in these fields. So for example, you just replace this Q by Z in these cases, and you get the number rings. And they can be realized as polynomial quotient rings in this case. So it turns out that if you have any number field K, then it has a canonical embedding into the Euclidean space Rn. And the image of the ring of integers becomes the lattice. And so you can think of it as the image of the whole field K is a dense set in Rn. But if you only look at the ring of integers, then it's discrete. So example, if you take Z adjoint square root of 2, then the image of R in the canonical embedding becomes the lattice spanned by these two vectors, spanned by the column vectors. So there's a canonical way of doing this. And now we're going to talk about, so now we have this lattice in Rn, and supposedly we want to base our security on some hard lattice problems by showing that the RLWE problem is as hard as these lattice problems. But maybe I'll first introduce what kind of lattice problems we're talking about.
So what was your definition of R in the previous slide?
Here?
The image of R, right? So your
The ring of integers.
So R is the ring of integers of K. So in the classical case, K is the 2-power cyclotomic field, and R is the ring of integers of K. So now if you have an arbitrary lattice in the Euclidean space given by a potentially very bad basis, then we'll recall this notion of lambda I, of the lattice lambda. That's the smallest number S such that the ball of radius S contains at least I linearly independent vectors in the lattice. So if you take I to be 1, that's the length of the shortest vector in the lattice. And now let gamma be a positive parameter. The gamma SVP, or the gamma shortest vector problem, is to find the lattice vector in lambda whose length is bounded by gamma times the shortest vector length. And the closest vector problem, called gamma CVP, is that you're given a point in the Euclidean space and you want to find a lattice point such that the distance between those 2 points is bounded by gamma. And then there's also this discrete Gaussian sampling problem called gamma DGS, where you're given a gamma and the lattice lambda and you want to output a sample from the discrete Gaussian. So again, I'll just briefly mention it again. A discrete Gaussian is where you sample each lattice vector, and the probability you sample a vector is inversely proportional to its length. Yeah.
So the hardness problem is the adversary is either in an actual discrete Gaussian or
here?
This one? Yeah.
So here the problem is actually to sample from this distribution. So it turns out to be hard.
But, I mean, the definition of the problem can't just be output a sample, because I can just output a number, and that's could be a valid sample of some Gaussian.
Yeah. So if you output, if you output a random number, that would be a sample from other distribution, but it's not guaranteed to be sampled from this particular distribution. So if you so maybe let's think about the most the one-dimensional case where you want to sample a discrete Gaussian on the integers. So there's no known way to do that because the integers is an infinite set, and you can only approximate that process.
I'm just wondering, so the actual hardness problem is stated in terms of distinguishing some algorithm that purports to do this from an actual true Gaussian.
Oh, so in the hardness proof, what they do is that they suppose they have an algorithm to output samples in this distribution, and then they show that they can have some sort of security reductions. So the proof in LPR is, to me, it seems like it's an iterative step that encodes also the bounded distance decoding problem. So it has 2 steps. One of them is reducing the bounded distance decoding problem to RLWE, and the other one is that if you have the discrete Gaussian sampling and RLWE, you can solve BDD. So, and then you just use them like again and again until you get to the point. So, I don't see. So maybe that's not a direct answer to your question, but the problem here, I think. So, are you asking if this problem is well posed, or?
No, I'm just asking what is the.
I think he's
how do
asking
you formally
something
define that
simpler.
problem?
What you suggest is probably right.
Okay.
He's just asked, the usual statement of these hardness problems has to do with like a decision version would be like,
Oh yeah.
can you distinguish whether this was a sample from, whereas you're talking about the constructive version or whatever would
Yes.
actually be to output a sample. So the decision version would be just to distinguish whether it's.
Yes, exactly. So, yes. So for all these problems, there is a I think for the first 2 problems, there is corresponding decision version. For DGS, I don't know yet whether there exists, but I think there could be.
So there, your goal is to produce an your adversary has to produce an algorithm that samples from something that's close to this distribution. So, for example, that tends to produce short vectors.
Yeah.
Yes.
Short
Yeah.
vector.
So Yeah, one intuitive way to see why this problem is hard is that when your gamma is 0, it's reduced to finding the closest vector. Because in general, you can consider this problem by shifting your lattice by a point. And if you shift it by so basically, when this gamma gets smaller, you're more likely to sample short vectors than long vectors. And this becomes a hard problem.
Yeah, so the point is that like it's very difficult to do this because the Gaussian sampling algorithm requires a very good basis.
Right, but I'm not asking about what it's hard, I'm asking about is this a distinguishing problem?
Oh, this one, no, this is not a distinguishing problem.
But then how do you, I don't understand the experiment that would invalidate the assumption.
I'm sorry?
Just like a computational problem requires you to find like the secret exponent, this like requires you to produce a sample.
Right, but if it requires you to produce a sample, I can output 0. That's a valid sample. Right? So there must be some way in which you would evaluate whether somebody.
Or for example, just using the basis, you can sample vectors in the lattice. They should be.
Yeah. So I mean, maybe in the I have some doubts about that, but I think maybe a good way to say that is that you want to consistently output samples from this. Like you want to have an algorithm that always gives you samples. So for example, if you want to keep outputting 0, then that's not a valid algorithm for this problem.
So the adversary has to produce an algorithm, so it's more of it's a non-falsifiable assumption. So there's no way if somebody gives you an algorithm without proof, then you can't tell if it produces negative technical distribution. But
Yeah. I mean,
assuming that it.
Right. So I guess you want to have like want to have an algorithm that produces a distribution that's like statistically indistinguishable from this discrete Gaussian.
Yeah. That would be a good way to define it. Mm-hmm. Yeah, because right. Because in the security reduction, actually what they do is that they assume they have this, and they use it to produce a lot of samples. So just having one is kind of not enough. But the way I say it, makes people wonder whether you just need to output like a random thing. And but thank you. Yeah, that's a good point. All right, and these problems get harder when gamma is smaller. So what are the main hardness results of ring learning with errors? So in the LPR paper, they proved that if the error width R is greater than square root of log n, then for any ideal in the ring of integers R, there is a quantum reduction from gamma DGS to RLWE. And here this gamma is given by Q over R times some constant. So like if you look at this formula, it basically says that when Q is large, then this problem is easier. And when R is large, this problem gets harder. So that's kind of the intuition. And that, the real security reduction is complicated, and as I described, it utilized this iterative step and the intermediate problem called bounded distance decoding. And one of them is quantum, the other one being classical. So if you really want to trace down the steps, then you have to iterate between quantum and non-quantum steps. And so this is for any number field and any ideal. If you restrict to the case of cyclotomic fields and the ring of integers in them, then you can replace the gamma DGS in the above theorem by soft O of NQ over R SBP. So that means that for these fields, if you can solve the RLWE problem, then you can also solve a certain approximate SBP problem. And in addition, if you also have the case where you have cyclotomic field and your prime is congruent to 1 modulo m, then you can replace search with decision. And I haven't talked about decision, but the decision RLWE problem is not to discover the secret S, but only to distinguish a set of RLWE samples from uniformly random samples. So that's sort of considered to be easier, but it turns out that if you have these two assumptions, then they're basically as hard as the same hardness. And there's an informal claim in this LPR paper where they said when the error is large enough, then you can do this sort of randomized rounding technique. And it shows that discrete error sampling is at least as hard as continuous. But there's no obvious direction going backwards. So basically what it means that if you have a discrete, if you have a continuous problem, you can round it to discrete version. And then if you can solve that discrete version, you can solve the continuous. But it's not clear whether that applies when the error is small, because the rounding produces some inherent noise that's irrelevant to the error size. So now, after these hardness results, what's left to do? Well, that's a very good question, because the paper did not really cover everything in the theory. So what if the error is small or the error is discrete? So these two are not discussed in the paper. And also, what if the modulus you choose is so large so that maybe the SVP problem is not hard? Remember, the SVP problem is only considered to be hard when you have like a polynomial bounded gamma. But if you have an exponential gamma, then, well, maybe that's easy. And also, what is the hardness of decision RLWE for general number fields? Remember, this is only established in LPR for cyclotomic fields. So if you want to choose your field to be something else, then you have to sort of worry about this problem. And also, another point is, in practice, homomorphic encryption schemes requires the error to be smaller for it to be more efficient. Because if you have, in general, what they say, a leveled homomorphic encryption scheme, you can only evaluate circuits of certain depth. And the number of multiplications you can do will depend on the error growth. And if the error is larger, then that means that you can do fewer multiplies before you have to re-encrypt everything again and start over. So it's definitely desirable to use smaller errors. So these are sort of the motivation of why we still study the hardness problem of general RLWE. And what is our goal? So one goal is to explore the boundary of security for all types of RLWE problems, regardless of whether the error is small or large, or it's continuous or discrete, or we're using the dual ring or the original ring. So I think that's something of value to the cryptography community. And also to the more practical side, we want to clarify the security of RLWE schemes used in practical applications. So like maybe we want to advise what's the parameter choice so that it's secure. Because if you want to use small errors, how small can you get before it gets insecure? So that's another question we hope to answer. Okay. So the goal very naturally leads to a study of the attacks on these RLWE problems. So in the third part of my talk, which is also the last part, I'm going to talk a little bit about attacks. So what are some of the attacks on RLWE? Well, the first way is to transfer the instance. Well, it turns out that there is a way to do that. You take RLWE samples, you can produce somehow like LWE samples, and then you can use their standard attacks on LWE, which forgets about the ring, and you have more generic ways of attacking. So you have linear algebra and BKW attack, Aurora and Guy, and Liner and Lauter. So I'll talk about them individually. And then, well, if you don't want to transfer to LWE, then maybe you can exploit the ring structure of R. So the first entry of my into this subject is this paper by Elias, Lauter, Osman, and Stange in 2015. And they talk about an attack using a reduction map from the ring R to a smaller finite field and do the perform the attack over there. So that attacks the decision problem. And myself, Lauter, and Stange in 15 paper, which we are submitting, and 6 following up, which we are submitting soon, we talked about attacks that further exploits the ring structure and also the ideals used in the reduction. So I'll talk about those. So how do you transfer an RLWE sample to an LWE sample? So if you have the ring of integers R, it has a basis over the integers. So you can think of it as n vectors, omega 1 to omega n. And if you fix that basis and you're given an RLWE sample A comma B, well, then you can write each coefficient of B in terms of this basis as a matrix acting on the secret vector plus the corresponding coefficient of the error. So if you think about it as the classical RLWE that I talked about, this is just taking the coefficients of the polynomials. So if you have two polynomials, then you take the first coefficient and the coefficient of x squared. So it gives you a bunch of linear equations, because this MA now becomes a matrix with known entries that are uniformly random. So that means from one RLWE sample, you actually produce n LWE samples. So here LWE is in quote because this MA, its rows are not really independent. They're actually permutations of the first row. So maybe, well, just let's replace this n by 1 if you want. But still, you can apply standard LWE attacks to solve RLWE. So how does this work? So assume this situation, that under a chosen basis, you have some coordinate E1 that's so small so that you will know that it's 0. So this is the first situation that's very bad, and people usually avoid it. Well, this is very insecure because, well, then what you have is an exact equation in S. So that means that once you have n samples, you'll be able to just perform Gaussian elimination to solve for the secret. So yeah, you just do linear algebra. Yeah?
Sorry, so why would one coefficient be known to be 0? Like we're sampling from a Gaussian section?
Yes.
Not 0?
So people are using sampling from a spherical Gaussian distribution. But the problem is that if you choose a basis, then the basis vector have different length, and the angles between them are different. So the coefficient doesn't really sometimes it doesn't really reflect what. So for example, if you have a really long vector, then although you are taking a spherical distribution, then the coefficient of that vector might still be very small, because if you want to scale it back into the ball you're sampling. So for example, this happens for this class of number fields k equals q adjoint nth root of 1 minus q in the crypto paper by Kristin, Kate, and other co-authors. So in this case, they have a basis of the ring of integers which is very skewed in the sense that the length of the basis vector form a geometric series. So I mean, then the longest vector basically never gets sampled. So this coefficient e, maybe en minus 1, is always 0 in their parameter range. So I mean, this for cyclotomic field, this usually does not happen. But for general number fields, I mean, anything can happen. So we want to exclude this case first, because that's the easiest part that you can break an RLWE system. So that's that. And also you have Aurora Guillen attack, which I think is really neat. Unfortunately, it's not super practical when the arrow becomes like not too small at all. But I think it's still valuable to discuss it. So what is it? If we assume the coordinate E1 is not 0, but now let's assume it takes values in some small integers. So maybe minus 2, minus 1, 0, 1, 2. Well, sorry, maybe not minus 2 and 2, just minus 1, 0, and 1. So it takes 3 values. Then you can take a polynomial f that vanish on this set. For example, here you can just take x cubed minus x. So x cubed minus x will vanish on all these 3 values. And now you have your equation where I have moved ma times s to the left-hand side. You apply f to the left-hand side, it becomes 0. So here you have eliminated the error. And this becomes an exact equation. But now what's the problem? Well, the problem here is that this is a linear form in the secret. With the secret has n components. And you're taking a polynomial of degree d and evaluating on it. So if you want to expand it, you get all kinds of monomials made of the secret of total degree d. For example, if d is 3, you may get s0, s1, s2, s0 cubed, s0 squared, s1, all kinds of things. So how many monomials are there? They're big O of n to the d. And then what you're actually doing is that you're solving a linear system in these variables, not the real s's. But now you need to do Gaussian elimination in O of n to the d variables. So, well, if d is larger than 5 and n is larger than 1,000, then it's not very practical. And for RLWE, you also have this BKW attack, which is sub-exponential. And again, it's an interesting theoretical attack, but in terms of practical performance, it's not that good. Well, what's the idea? Well, the idea is you want to still do Gaussian elimination, but remember now you have some error term in the equation. So every time you do an addition, like if you want to add a row to another, then it increases the error. So the error basically doubles. And if you want to multiply a multiple of the row to the other, then it gets worse. So you want to do it by using as few row operations as possible. And also you want to keep a dictionary, like maybe for the first 10 coefficients of A, and you store everything in a database, and you keep getting these samples until two of them happens to be the same. So you can already see that this is an exponential algorithm because you have to wait kind of exponential times, like maybe 2 to the n. So if you have two equations where the first 10 coefficients are the same, then you can just subtract them, and then you have eliminated kind of one part of your equation. So you keep doing this, and you organize yourself correctly, then you have an algorithm to solve RLWE. But I mean, this also only works when the error is small enough. So what is the third point, which is a paper published by Lyubashevsky and Lauter in the audience in 15, where you assume that the modulus Q is not polynomial in the dimension of the lattice, but it's exponential in n. So in this case, well, the closed vector problem, you can turn the problem into a gamma closest vector problem on certain n plus d dimensional lattices. So here d, I think, is the number of samples. So you have a big lattice, and you can solve a closed vector problem on this big lattice, and that will give you exactly the secret back. And this works when the modulus is exponential in n. So in the paper, they have concretely coded attacks that succeeds like in a matter of hours. So how do you solve this gamma closest vector problem? You can use a standard lattice algorithm like RLWE or Babai's algorithm. And the complexity is polynomial in n. So now let's go to the attacks that actually exploits the ring structure of the corresponding RLWE problem. And what this turns out to be harder to find. And in this very nice paper by Elias, Lauter, Osman, and Stange in 15, they assume that you have the ring R as a polynomial quotient ring of z of x quotient out by some polynomial where you assume the polynomial evaluated at 1 is 0 modulo the modulus Q. So this doesn't usually happen, but it sometimes does. So when it does, you consider the reduction map from the ring R to the finite field of Q elements, and it takes any polynomial to its evaluation mod Q. So because you have this assumption, this pi is a valid map. It is well defined. And then you assume something on the number field that if you take the arrow E and apply the reduction map pi, then it won't go to the uniform distribution in the finite field FQ. So I mean, also this doesn't happen for every number field, but let's assume it does for the moment. And then the idea of attacking is just to loop through all guesses of the secret modulo, of pi of s, because pi of s can only have q possibilities. So looping over q possible choices is actually not that bad. And then if you have a guess, what you do is that you compute the hypothetical error, because if this guess is correct, then you're getting pi of e. If it's not, then you're getting maybe some garbage. But so you can detect whether this is a garbage by using the assumption that pi of e takes small values. So if you happen to get something with large values, well, maybe you try again. If you get it again, then probably this is not the good guess. And then you keep doing this until you get only one G left. And the complexity is big O of Q, because you're looping over Q guesses. And some examples of vulnerable number fields also include this case. But notice that the linear algebra attacks also apply to this class of number fields, but only when the error is small enough. So currently I think that the techniques used in this paper can be applied even when the linear algebra attack doesn't. Okay, so now finally there's a slide with my work. So I'm glad that we come to this point. So now let's assume a different kind of vulnerabilities that can happen. Let's assume that there's a prime ideal Q in R, and the Q has residue degree F larger than 1, maybe 2. So, well, this may not mean a lot, but basically it says that you have a reduction map from R to this quotient ring, which is isomorphic to the finite field of Q to the F elements. So this is not a prime field, but rather like an extension of FQ. And we assume that the error is more likely to lie in FQ, actually, not than the uniform distribution. So for example, if F is 2, then the uniform distribution would yield a probability of 1 over Q, because FQ squared has cardinality Q squared. But if for some reason the error is more likely to be in FQ, then we can detect this by sort of basically the same idea. Like you loop over everything in here and you try to compute pi of E. Yeah, so that's, and then you use some kind of statistical test like chi-square, or you compute the KL divergence, or there are various ways you can check for uniformness. If it's not uniform, then you know your sample is RLWE. And I think I forgot to mention that these two attacks are on the decision problem. But here, this one can be applied to a class of number fields where we actually also proved a search to decision reduction, and we attack the search problem. But yeah, this complexity is big O of n times q to the 2f for decision, and n squared q to the 2f over f for search. So if f is 2, this is still like relatively small. And there has been, in a 2016 paper we're preparing, I think we can get this f, can remove this too. Yeah?
So is n still big? What is roughly what is n?
Rough, so
1,000, n equals 1,000, like 2 to the 10 or something.
yeah, so the goal is really to get n to 1,000. So in our paper, I think the maximum we get is about 144. So, but I think in general we can get examples of arbitrary dimension.
And what is, can you give intuition for what it means for ideal to have residue degree f, or like an example?
Oh, so yeah, for example, if you take the Q adjoint I, that's a quadratic field, and an ideal has residue degree 2 if and only if it's equivalent to 3 modulo 4. So for example, if you take the prime ideal 3, so the ideal generated by the number 3, then that has residue degree 2. So basically, residue degree just means that this quotient ring, this quotient field is equivalent to, is isomorphic to the finite field of Q to the F elements. All right, so that's the attack, but is any, so are there any examples? So there are some sub-cyclotomic field we found by searching, and also one can explicitly construct a family of quadratic extensions of cyclotomic fields that are vulnerable to this attack. So here are some examples. Yeah, so these are actually the improved runtimes, so where we did in the second paper. So you can see that in this 144-dimensional instance, and solve it in a matter of maybe a little less than 2 hours.
Sorry, when I said 1,000, I meant that's what we use in practice as a minimum. N would be 1,000.
Yeah, but I mean, this table definitely can continue to, and it actually won't, yeah. Really, I think in the complexity, what matters more is the Q. So if Q gets large, then because it has this 2 times F factor, then it will mess up it will take the running time, well, it needs to be longer. Okay, and the other attack we had in the paper is that it's very specialized to the prime cyclotomic field. So if we consider a prime P and the P cyclotomic field, then there are 2 attacks we derived. So one of them is when we assume the error is discrete. So in this case, we we can only attack when the modulus is exactly equal to p. So this is a very special case. But when it happens, there's some vulnerability because then also you have this f1 equals 0. So one can just directly apply the previous attack in a paper by 4 authors. And also, in this case, there's a prime ideal behind the scenes, and it's ramified, which is some technical term, but that means that we can only attack decision but not search. But in this table, everything here, we can attack search. And now we come to continuous error, and it turns out if the error size is small enough, then we can attack any modulus. So let's make no assumption on Q, and suppose the error is continuous. And then let beta denote this element zeta p minus 1, and we have this map that, so you can think of the domain of this map as the Euclidean space Rn. So that's basically where the error lies. And we take it and map it to R by just taking the first coefficient of a polynomial in beta. So here everything can still be represented as a polynomial in beta because R is equal to Z adjoint beta. So powers of beta form a power basis for the ring. So then very curiously, under this map, you take the prime ideal P, then it will go to P times the integers. Well, this is just because the prime ideal P is generated by beta. And also, we know something about the dual. So here, the work I'm doing is trying to directly attack the dual setting in the original paper of RLWE. And you have an error. You can scale it so that the second coordinate lies in this Rn modulo Q times the prime ideal. And then this part will vanish if you apply the map rho to it, because once you scale it, APS becomes APS lies in the prime ideal frac P. So then you can test for uniformness, because if you start with uniform samples, you're going to have some uniformly random dots in the circle. The circle is R mod PZ, or R mod Z if you want to scale it by P. So if your error happens to be small enough, then you can check whether the samples you get are uniform. So this is sort of the same idea. So what's kind of surprising is that it actually works for small errors. So here I want to comment that, remember, if we recall the LPR security proof, then here you would really want these numbers to be about square root of n for their security to apply. So that means that the parameters we can attack here is very much below their security parameter. So we're not breaking their assumption. We're solving a hard lattice problem. So but this is a concrete way of exhibiting like what is the security situation if your error is not large enough. So here, if your error is square root of n smaller than what they claim, then it's very easily breakable. And you can see the runtime, even though you have a 1,000-dimensional lattice, this runtime is very fast. But this only attacks the decision problem. So now we have surveyed these all kinds of attacks. Maybe I'll give a kind of a summary of what the security situation is currently. So first, let's talk about continuous errors. So in that case, I think although in the original paper they didn't do this, but still it's to compare different instances, you have to sort of multiply and normalize your error weights because you're dealing with different lattices and their sparsities are different. So it doesn't really make sense to compare the error weights without talking about the lattice and how sparse the lattice is. So here I'm basically rescaling by the lattice covolume. And the LPR paper proved that its claim for cyclotomic fields where you have polynomial modulus and totally split, which is the same as saying 1 modulo m, then ignoring this factor because it's really small, if you have square root of n error, then it's guaranteed to be as hard as some lattice problem. And also, if you have any field and polynomial modulus, then you are required to have the discriminant at least to the root discriminant of the number field. And that's going to guarantee the security. So notice this depends very much on the field. So there's no a priori way to say. And then our attack is that if you have prime cyclotomic field Q zeta p and your normalized error width is about 1, then this is not, the decision version is not secure. And if you have time to expand this table, then for any number of fields, I think that if you have anything that's smaller than this, then the security is not clear. And now for discrete errors, I think although discrete errors is not, it's used in practice, but surprisingly, there has not been a lot of papers in the literature talking about their security. So they have these kind of rounding results, but they always assume that you already have a continuous model. And also, people do acknowledge that if you discretize a continuous error, that's not the same as directly sampling from a discrete distribution. And in practice, that's what people do. You don't do this extra round of rounding process. So here are some summaries. So maybe, yeah, all of them are basically already described in previous papers. I'm just trying to put it all together to see that. So with polynomial modulus and the normalized error width to be around 1, there's a lot of instances where this is not secure. But what happens is that if you take cyclotomic field and if you take a modulus that's totally split, then even if you have small error, then it's still likely to be secure. So this is something that's not in the table, but we're just saying that, so from this table, I think one takeaway is that for general number fields, the security very much varies on the field structure and the modulus and the error. But for cyclotomic fields, the situation can be might be much more simplified. So yes, and some future work. So as I just mentioned, there's a possible way, and I just had this idea like a week ago about proving the hardness of RLWE problem underlying real-world homomorphic encryption schemes. So for example, like the BGV scheme used in IBM's HElib library, or the Yashi scheme and Yashi prime used in Microsoft's SEAL library. So there, you really have a lot of assumptions on the parameter choice. You're using the cyclotomic fields, or maybe like you're even using the 2-power cyclotomic field. Your modulus is completely split, and you're using the non-dual ring and discrete error and small secret. So everything is very restrictive. So in that case, I think one might be able to prove that in this case, RLWE is hard without reducing to the lattice problems. So you can show, maybe using information theory, that decision RLWE is equivalent to RLWE mod Q. So this is another technical term, but basically it says that when you take the error mod Q, like we did in the previous slides, then it becomes uniform or not. So the two problems are likely to be equivalent, and then you want to show that this is impossible or this is hard by showing that the error modulo of a prime ideal frac Q is pseudo-random, that in that any attacker cannot distinguish it from the random, from the uniform distribution with a non-negligible advantage. So there are two possible ways to approach this. One of them is using Regev's smoothing parameter, which he introduced in his joint paper with another co-author in 2004. And so this turns out to be very useful, and I can, I think I can use it to provide some kind of upper bounds on the statistical distance. And another possible way is to use Fourier analysis and properties of this Jacobi theta function. So this is kind of more from a number theoretical point of view, but you want to prove that certain distributions on the finite field is close to uniform, and that statement can be translated into taking the Fourier transform of the distribution that is close to the delta function. So because the Fourier transform of uniform is delta. And then you want to bound the difference between that new function and delta, so that actually the Fourier transform turns out to be this function in the 2-power cyclotomic case. So I think it's kind of surprising and exciting. So I just have some very rough sample result from these preliminary calculations. But if you have the dimension equals 128, your modulus is 257, and your error width is about, sorry, this is 1 hour mark. But this is my last slide, so I think I'm not too much over time. And this is the error weight, and this is the number, a very rough, very loose lower bound of the number of samples you need to distinguish RLWE mod Q and uniform mod Q. So you can see that even if so here maybe n is small, so there's no like real difference between square root of n and 1. But if you let n to be larger and use a better analysis, I think that it is possible to do more. So that concludes my talk, and thank you very much.
Questions?
Yeah.
So overall, it seems like takeaways for designing these systems is that you have to be very careful in choosing your field. Because choosing the wrong field is definitely bad, and that there's a substantial gap in the errors. If you make your errors very small, then that's also bad. If you make them what people are using today, it seems probably okay.
Yeah. I mean,
do you have a sense for are they about it? What do you expect that's about a lower bound, or do you think there's a lot of room where you can use smaller errors but not as small as the?
So I think people, the errors people use today. So in practice, people usually use cyclotomic fields. So that's good. They don't really try like a random new number field. So the error they use, I think it goes between a constant and root n. But I think root n. So root n is really this continuous analog. They expect root n to be secure, but in the discrete world, it's my work. I think what I'm trying to show is that you have something smaller than root n that might still work, but what people actually is doing is that I think they're using small constants. But I mean, there's a difference between asymptotics and actual instances. So like if you're using 1,000-dimensional lattice, then the difference between root n and 1 is still not large. So I mean, but here, I think what I can do is instead of giving asymptotics, producing an explicit number that you need to go above to ensure security. So, but I mean, for the schemes they use in practice, I mean, once I have this machine, then finished, I'll just plug in the numbers. But that's the next step.
If you had to guess, you place a bet, would you say that the values currently being used are insecure, or are too conservative, or about right?
I think they're secure.
Yeah.
I just can't resist making a comment on that point, though. There's a huge difference between what IBM does and what we do. So they use not only small error, but also small secret and sparse secret. And the small secret and sparse secret have potential weaknesses. We don't know them. Mm-hmm. But the small error also is an issue. And they get a huge amount of efficiency from those combination of those three things, which we don't do.
So you think they may be too aggressive?
Yes.
Yeah. So IBM,
And they also use general cyclotomic fields, not 2-power cyclotomic fields.
Yeah, I think an immediate next step for me is to prove it for 2-power cyclotomic fields. For general cyclotomic fields, this we need to modify these steps. But I think it's still doable, but I think it's more complicated.
Yeah, so I think the point is that actually we're using in practice very small standard deviation per error, like 3 point something, and but like there are really no clear attack paths that would make that vulnerable in any way. Like there's no clear reason why 3 point something would be any more secure than, or any less secure than like 100 standard deviation or 1,000. I mean the only case where I know that there would be something is when the error is binary, because then you can use some other tricks. but even then it's not like a total break. It just reduces the security by a little bit. And then also it's true, like Ha said, like the security reduction even in Regev's original paper, it works when the standard deviation is roughly square root n, right? I mean, it has to be at least square root n.
Yes, yes.
But then there's also this like other requirement, sort of, because like you pointed out in one of your slides, the gap SVP that you get from that is like, the gap is like NQ divided by the standard deviation roughly. So, I mean, this NQ divided by the standard deviation must be small. So this means that in fact this standard deviation has to be, I mean, this NQ over standard deviation must be like polynomial in n. And this means that this standard deviation that's dividing NQ must be like size q. So in fact, there is this kind of hidden thing there that you need for the security reduction to make any sense, that the standard deviation is linear basically in q, but also bigger than square root n, right?
Yeah. I mean, for square root of n is sort of the literature lower bound. So here you're secure, and there are a lot of attacks when your error is super small. So here you're insecure. So inside there's nothing up to date, but yeah, I think there's a lot of room to work on.
Any other questions? I'll ask another one if anybody else has. So, as you kind of pointed out, if you think of the rings that could potentially be used, you have the 2-power cyclotomic rings, which is what Microsoft implementation uses. You have the general cyclotomic rings, which is what IBM uses, and then you have all the other rings. And from a lot of the results you've shown here, there's really no reason to venture out into this area of all these other rings, because we already see all these problems. So we've got good efficiency here with these two cases. So we can kind of like disregard all of these rings from a practical point of view if you're an implementer. And now you've got these two choices, the IBM and the Microsoft choices. And you talk about this kind of informal result from LPR that says why you think you can go back and forth between this continuous and discrete error. So can you comment on the difference in the 2-power cyclotomic versus general cyclotomic, going back and forth between discrete and continuous error?
Yeah. I mean, so in the LPR paper, like even informally, they didn't. They have to require the error to be large enough, like sort of at least square root of n, for there to be any relationship between continuous and discrete, because the rounding process, the noise produced by the rounding process is really not controllable by the error distribution itself. It's a function of the field and the modulus actually, and the secret. So I mean the thing is this internal noise makes the reduction hard. So I think both in the IBM implementation and in the Microsoft implementation, the error they use are below the security threshold. But so that is one of my main motivations for this, because 2-power cyclotomic fields, instead of general prime cyclotomic field, which IBM uses, is more likely to be secure under this parameter range. For prime cyclotomic field, I think it's not clear. The reason is that the way of sampling they use is actually, I think the way of sampling they use is not exactly the RLWE distribution. So I think they sample from some polynomial basis, but that would be a different distribution. So this basically no hardness results apply to their case. So you can't say, I mean, at least right now I can't say whether the IBM is secure, or I don't have any guesses. But for the Microsoft implementation, I have confidence that even within their parameter range, it is still secure, and it's possible to prove that. And that's because there's a big difference between 2-power cyclotomic field and general cyclotomic field. In that the 2-power cyclotomic field is kind of the most most classical case where everything is reduced to a polynomial basis, and it just won't produce any weird geometry. So I think that's the main difference.
Any other questions?
Like how it gets.
Thanks.